EW control is purely distributed. There is no special control device. The nodes themselves are the controllers. For example, if I wish to control a battery, as we will see in a following example, the node monitoring the battery is also responsible for carrying out the control. When is EW control required? EW control is not designed to carry out typical system control. Building systems almost always have sophisticated controls. A heating system typically uses various thermostats to control its function. An embedded controller always comes together with the installation of such a system. There is no fundamental reason that EW control could not be used in such cases. There is, however, little scope for such control action. Where we consider EW control as unique and particularly useful, is the case of energy flow control and optimization. For example, if I have a PV system feeding to the grid, a battery feeding to the grid and also connected to the PV, how do I optimize this system? This is a typical scenario for EW control and is a scenario that will more and more appear every time there are multiple energy channeling options and an optimization decision is required. This is largely what smart grids and smart energy are about, at least when seen from the demand side. Thus, as these smart energy concepts come to the mainstream, EW control will become more and more relevant. What data does this control action depend upon? The control algorithm will almost always depend on data collected by the node itself. For example, in our battery control, the control action depends on battery load status, which is a parameter locally sourced. What is very interesting, however, is that the control algorithm can easily depend on data coming from other, remote nodes. The routing protocol that has been developed allows nodes to send data to other nodes. For example, a specific control action may depend on meteorological data. These data need to be sent to the control node from the respective environmental node. They can then be used by the control algorithm and used to generate the required control output. What is required for a node to be a controller? There are two requirements. First, the node needs to have some programming capacity that can host the control code. Second, it needs to be able to generate control outputs, digital outputs. How can we provide for node programming capacity? There are two options here. In simple control algorithms, code of up to 8 kilobytes, they can be hosted on the microprocessor off the radio chip itself. This has been the case of the example that will be presented later. In more complex cases, we have provided for a special baseboard design with a separate on-board microprocessor, so-called SoC, Programmable System on Chip. This is a very low-cost microprocessor, typically around 5 to 15 euros depending on specifications. This controller reads in the data from the radio, both the local as well as the remote data, runs the control code, generates the outputs and sets the respective digital outputs on the baseboard. How are digital outputs generated? Our baseboard designs have currently 2 digital outputs. Note, these outputs are very low voltage and need to be amplified to be able to drive the control relays. The amplification circuit is a very low-cost circuit, with a cost a percentage of €1 and comprises transistors and resistors. We have installed a battery next to the PV system, and the simple control algorithm implemented is as follows. 1. Upon user action, the grid is connected to the battery and loads it up fully, 100%. 2. When the battery is fully loaded, then the PV system is disconnected from the inverter. The battery is connected to the inverter. 3. When the battery is discharged to a certain percentage, 97%, then the battery is shut off from the grid and the PV system connects again to the grid. This implementation required, besides the existing PV panels, inverter and battery, the following installations. 1. An EW controller node, that is a node monitoring the battery and in fact 5 parameters. Charge status. Energy going in. Energy going out. Current flowing in or out. Voltage. This node was based on a EW DC energy meter. The node measures all above data, transmits them to the gateway and also carries out the control algorithm setting, resetting, in this case, just one digital output. 2. The electrical cabinet that is put between the PV inverter and the EW controller. This cabinet has essentially 2 key power relays and a number of control elements, timers, etc. The electrical drawing is shown here. The relays controlled by EW control are the RP relay connecting the PV panels to the inverter, and RB relay connecting the battery to the inverter. The timer contacts shown are used to provide some delay between the switching of the 2 relays and connecting the 2 power systems, PV, battery, to the inverter. This time delay is necessary to avoid arcs, etc. The power cabinet that implements this drawing is shown below. The 2 relays, shown in the green circle, and the power supply, shown in the red circle, are located at the left of the cabinet. To their right, shown in the yellow circle, one can see the 3 contacts shown on the previous diagram. At the right end the timer, shown in the black circle. This power cabinet is necessary to make sure that when the battery connects to the grid, EW control action set to 1, the PV system is shut off, otherwise short circuits will result. When the battery is disconnected from the grid, EW control action set to 0, the PV system is again connected to the grid. The image below illustrates our EW DC meter control node, 12 volts, on the top of the battery. Unfortunately there is now proper casing yet designed and this results to a small cable mess. There are 3 cable sets here. The 3 thick cables, shown in the yellow circle, are the power cables coming from the battery poles. The EW energy meter measures in the real time the 5 parameters discussed earlier. In the red circle one can see the control cables which take the control output and amplifies it by means of the transistors at the front right corner of the image. After the amplification the cables go to the above control cabinet. The many thin cables at the back shown in the green circle, run into the radio unit that cannot be seen here. In this case the radio not only transmits the data to the gateway but also implements the control code that we will describe below. This side photo of the battery shows the radio unit to which the EW DC meter EW control unit is connected. We will now illustrate the control action. At this very moment, on 9th of July 11:49, the battery node reports the following data. Real time. 9th of July 11:49. Because in the past 24 hours some testing was carried out, the energy in parameter reports a small figure. This parameter shows in an accumulative way the energy that entered the battery over the last 24 hours. However, at this moment there is no current flowing in or out. At this moment we can also see that battery's state of charge is 73%. Let's come back to the dashboard in 2 hours to see the situation. Real time. 9th of July 13:32. Here is the situation of our battery after about 2 hours. We can see the battery loading, current is flowing in, approximately 3.7 A, whereas the total energy in has raised from a residual value of 449 mWh to a now 72 Wh. Our battery state of charge is now 94%. Currently EW control code requires the battery charge to rise up to 100% before the switching takes place and the battery is connected to the inverter and the grid, and discharges its energy. As soon as this happens, the EW control will connect the battery to the inverter and we will be able to see the battery discharging. The energy out metering will start rising, the current will change direction and the charge will decrease. We will see this in a screenshot, in about a few hours. Real time. 9th of July 14:06. EW control in action. The battery has now switched to the inverter and energy flows out of it. This will carry on till the battery is discharged to the value set in the control algorithm, 97%. At that moment the battery will be disconnected and the inverter again connected to the PV panels. This diagram from the EW dashboard shows energy out increasing and the current parameter that has now changes direction, outgoing. Real time, 9th of July, on 14:12. This diagram, a few minutes after the previous one, shows the pattern of current, first charging the battery and then discharging it during the full demo period. Note the battery discharge rate reduce further to 98%. It will take about 30 minutes to come down to the control set value, 97%, where the battery will be disconnected. Real time. 9th of July 14:46. The battery has reached 97% and, as the EW control suggests, battery has disconnected from the inverter. We can also see the full battery charging, discharging cycle, as dictated by the EW control in the following figure. We see here the initial charging phase, from the 73% value up to the 100% and then its discharge to 97%, at which moment it was disconnected from the inverter.